Every atom in your body holds a secret from the dawn of time. We are going back to the very first moments, to the creation of the universe's first light elements. This journey will reveal 30 astonishing theories about how hydrogen, helium, and a trace of lithium were forged from nothing. You will discover the true cosmic recipe that built every star and planet, including our own. We will question if the early universe was perfectly smooth or filled with strange lumps. We will explore whether ghostly particles and unseen dark matter stirred the cosmic pot. What single idea about our cosmic beginning feels most compelling to you? The universe was born in a firestorm of pure energy. For a fleeting 3 minutes, everything that would ever be was contained within a searing hot, impossibly dense soup. This was not the universe of vast, empty space we know today, but a single, roiling point where particles collided with unimaginable force. In this chaotic forge, the first building blocks of matter were about to lock into place through a process called primordial nucleosynthesis. Think of it as the universe's first and most fundamental cooking lesson. As the cosmos expanded at a furious rate, it also cooled, just like steam rising from a pot loses its heat. This cooling allowed the most basic particles, protons and neutrons, to finally grab hold of one another. Protons, which are simply lone hydrogen nuclei, began fusing with neutrons to form new, heavier cores. The main dish was helium, the very same gas that fills party balloons. This frantic cooking session was brutally short. The universe expanded so rapidly that within those first 3 minutes it became too big, too cool, and too thin for the particles to keep smashing together. The cosmic kitchen simply shut down, leaving behind a specific recipe. For every 16 particles, about 12 remained as simple hydrogen, and 4 were fused into helium, with only a tiny sprinkle of lithium left in the mix. This was the primordial fingerprint, the foundational chemistry that would set the stage for everything to come. Every star that ever shone, every planet that ever formed, carries this original flavor deep within its core. But what if that cosmic kitchen was not a single, uniform pot? The standard model presents a smooth, evenly mixed infant universe. Yet a compelling alternative, the inhomogeneous Big Bang theory, dares to suggest the cosmos was born lumpy. Imagine a pot of soup just beginning to simmer with thick, dense clumps of ingredients floating in a thinner broth. These were not mere imperfections. They were cosmic hotspots, regions of intense density where the rules of nuclear cooking could have been rewritten. In these crowded pockets, protons and neutrons were packed so tightly that their frantic collisions might have forged elements the standard model cannot account for. We are talking about traces of heavier elements like beryllium or boron, substances that should not exist in a perfectly smooth primordial soup. The very ratios of hydrogen and helium we take for granted could have been different from one region of space to the next. This theory challenges the foundational idea of a uniform beginning. It paints a picture of a more chaotic, textured infancy for the universe, where the first elements were not stamped out in a single, identical mold, but were crafted in unique local forges. So the next time you look up at the night sky, consider this. The ancient helium in a distant star might tell a slightly different story than the helium in our own sun, a silent testament to a lumpy, unpredictable birth. Those ghostly particles from the beginning have left their own faint fingerprint on creation. While the dense soup of particles was busy forging the first nuclei, the universe was flooded with trillions upon trillions of neutrinos. These are not like the protons and neutrons you find in an atom's core. Neutrinos are phantoms, able to pass through entire planets as if they were not even there. In that searing early cosmos, they were everywhere, and their sheer presence exerted a subtle but profound influence on the cosmic kitchen. The key was their effect on a single, critical balance, the neutron-to-proton ratio. Think of this ratio as the master dial controlling the universe's helium production. A slight turn one way or the other would have resulted in a completely different elemental mix. Neutrinos, through their weak interactions, were constantly nudging that dial. They could transform a neutron into a proton or a proton into a neutron in a frantic subatomic dance. This dance determined how many neutrons were available when the universe cooled just enough for helium to form. Now consider a twist. What if these primordial neutrinos were not all identical? Different flavors or energies could have made this dance slightly more or less efficient. A universe with slightly hotter neutrinos, for instance, might have tipped the balance, leaving fewer neutrons available. The result would be a cosmos with significantly less helium than we actually observe. The fact that our universe ended up with the precise helium abundance we see is a powerful clue. It tells us that the ghostly neutrino background must have had a very specific character, its properties fine-tuned in a way that allowed for the nuclear recipe we depend on. This theory suggests that the invisible neutrino sea, a relic we can still detect today, was an active and essential chef in the primordial kitchen, subtly seasoning the first elements of everything. Before particles could form atoms, they had to form themselves. Our story of creation must step back even further, to a time before protons and neutrons were stable entities. The universe was an ocean of pure potential, a seething, impossibly hot soup known as the quark-gluon plasma. In this state, the fundamental bits of matter, quarks, and the force carriers that glue them together, gluons, roamed freely. They were not bound into any permanent structures. This was the ultimate cosmic chaos. Then, in a flash, the universe expanded and cooled past a critical threshold. It was a phase transition as profound as steam condensing into liquid water. This quark-gluon plasma froze. The free-roaming quarks and gluons suddenly found themselves locked into new, stable combinations. They formed the very first protons and neutrons. The precise speed and smoothness of this transition were everything. If the freeze-out happened too rapidly or with turbulence, it could have created a slight imbalance in the number of protons versus neutrons. Think of it like a sudden frost settling over a lake. The pattern of ice that forms depends on how quickly the temperature drops. A quick, sharp freeze creates a different structure than a slow, gradual cooling. In the primordial universe, the character of that frost determined the initial ingredients available for the next step. The proton-neutron ratio set during this fleeting moment became the foundational budget for the entire 3-minute nucleosynthesis that followed. A slight tilt in that initial balance would have cascaded through the entire cooking process, dramatically altering the final amounts of hydrogen and helium we observe today. The silent, invisible decay of the quark-gluon plasma may have been the first and most decisive act in our elemental story. This delicate balance of forces feels so permanent, so absolute. But what if the rules themselves were not always written in stone? The variable constant theory proposes a truly radical idea. The fundamental strengths of nature's forces, the very numbers that define our reality, might have been different in the universe's first moments. Think of gravity, the force that holds planets in orbit, or the weak nuclear force which governs how particles decay. We take their power as a given and unchanging fact of physics. Yet if the weak force had been just a fraction stronger during that crucial 3-minute window, the consequences would have been catastrophic for the universe we know. A stronger weak force would have made it drastically easier for neutrons to decay into protons. The cosmic kitchen would have been flooded with protons, while the supply of neutrons, the essential ingredient for helium, would have dwindled to almost nothing. The result would be a cosmos filled almost entirely with hydrogen, a universe without the helium needed to fuel the first stars. On the other hand, a slightly weaker weak force would have had the opposite effect. Neutrons would have been far more stable, tipping the balance the other way. This could have created a universe dominated by helium, a strange and sterile place where the simple, stable hydrogen atom was a rare novelty. Our existence hinges on a knife's edge. The force was tuned to a perfect value, allowing for just the right neutron-proton ratio to create the elemental mix we see. This forces a profound question. Are the constants of nature truly constant, or did they simply settle into the only values that could ever allow for planets, for stars, and for us? The first light elements are not just a relic of the past. They are permanent evidence that the laws of physics from their very first moment were precisely set for life to one day emerge. This fundamental question of why anything exists at all brings us to the baryogenesis puzzle. For every particle of matter created in the Big Bang, an equal particle of antimatter should have been born. Think of antimatter as matter's perfect mirror image twin. When a particle meets its antiparticle, they annihilate each other in a flash of pure energy. According to all the basic rules, the universe should have cooked up equal amounts of both, leading to total mutual destruction. Every proton would have met an anti-proton, every electron an anti-electron. The entire cosmic experiment would have ended almost as soon as it began, leaving behind a silent, empty expanse of light. Yet here we are in a universe made of stars, planets, and people. Clearly, something went very right. For some reason, an asymmetry was written into the laws of physics. For every 1 billion pairs of matter and antimatter that annihilated, a single, solitary particle of matter was left over. That 1 in a billion survivor is the reason you and I and everything we see exists. This slight excess of matter, this broken symmetry, is what physicists call baryogenesis. It was the ultimate act of cosmic favoritism, and it determined the entire budget of protons and neutrons available to build the first elements. Without that tiny, inexplicable imbalance, there would have been no hydrogen, no helium, no atoms of any kind. The primordial nucleosynthesis that followed would have had nothing to work with. So what cosmic mechanism could have tipped the scales? One compelling idea is leptogenesis. This theory suggests the imbalance might have started with ghostly neutrinos. Heavy, hypothetical neutrinos in the early universe could have decayed asymmetrically, producing slightly more matter than antimatter. This initial bias in the leptons, a class of particles that includes electrons and neutrinos, could then have been transferred over to the quarks that make up protons and neutrons, seeding the matter excess we see today. Another proposal is electroweak baryogenesis. This scenario plays out during another cosmic phase transition, when the electromagnetic and weak forces were still a single, unified entity. As the universe cooled and this force split in two, it could have created bubbles in the fabric of space-time. The walls of these expanding bubbles might have acted like a filter, preferentially creating or reflecting matter over antimatter. The entire observable universe could be the aftermath of one such bubble, a single region where the balance was accidentally and perfectly broken. The search for the answer continues in particle colliders and deep underground detectors, trying to recreate the conditions that allowed our universe to be. The existence of every atom is a permanent reminder of a primordial crime, a theft of matter from the jaws of total annihilation. That 1 in a billion surplus of matter set the stage, but it took a far more dramatic event to give the universe its texture. An unimaginably brief period known as cosmic inflation occurred when the universe was less than a trillionth of a second old. In that fleeting moment, the cosmos underwent a growth spurt so violent that it expanded by a factor of 1,000,000 trillion. This was not a gentle swelling but a runaway stretching of spacetime itself, and within that furious expansion, something miraculous was imprinted on the cosmos. The vacuum of space is not truly empty even today. At the quantum level, it seethes with tiny, fleeting fluctuations where particles and energy pop in and out of existence. During the inflationary period, these minuscule quantum jitters were caught by the stretching fabric of reality and inflated to enormous sizes. What were once subatomic ripples became vast hills and valleys in the density of the young universe. These are the inflationary perturbations, the primordial seeds from which all structure would grow. These slight overdensities, regions where there was just a little more matter than the surrounding area, became the preferred locations for the universe's first cooking. When the 3-minute epoch of nucleosynthesis began, these denser patches had a slight advantage. With protons and neutrons packed a little more tightly together, the nuclear reactions that forged helium could proceed just a bit more efficiently. The result was not a perfectly uniform spread of hydrogen and helium. Instead, there were the faintest of variations, microscopic differences in elemental abundance that were directly tied to those initial quantum seeds. A region that started slightly denser would end up with a marginally different mix of the first elements. These tiny chemical fingerprints were then frozen into the fabric of the cosmos, carried along for the ride as the universe continued to evolve. They were the blueprints written in the language of hydrogen and helium for everything that was to come. The vast cosmic web of galaxies and clusters we see today, with its great walls and immense voids, is the grown-up version of those infant density variations. So the helium in a distant star does not just tell us about the conditions 3 minutes after the Big Bang. It also carries an echo of a quantum whisper from a time almost too early to comprehend. The universe's largest structures were born from its smallest possible fluctuations. The silent presence of dark matter may have been the universe's unseen chef. We know this mysterious substance outweighs all the atoms in the cosmos by a factor of 5, a ghostly giant shaping the universe from the shadows. Its influence is felt in the rotation of galaxies and the bending of light, but its true nature remains one of physics' greatest puzzles. A fascinating question arises. Could dark matter have been active during the universe's first 3 minutes, subtly guiding the recipe for the first elements? Some theoretical models suggest that certain types of dark matter particles were not completely passive in that primordial forge. Imagine a scenario where these particles were unstable. Billions of years before they clumped into the halos around galaxies, they could have been decaying, releasing bursts of energy into the seething cosmic soup. This sudden injection of heat would have been like turning up the flame under a simmering pot. It would have changed the rate at which the universe cooled, a critical factor controlling how long protons and neutrons could find each other and fuse. Even a slight delay or acceleration in the cooling rate could have altered the final yields. A slower cooling might have allowed more neutrons to be captured, producing a bit more helium than the standard model predicts. Alternatively, a specific type of dark matter interaction could have directly affected the neutrons themselves. If these ghostly particles scattered off neutrons, they could have effectively trapped them, preventing them from participating in the formation of helium nuclei. This would leave us with a universe that has less helium and more leftover hydrogen. The precise abundances we observe today, the very fingerprints we use to test our theories of the Big Bang, could be pointing to an invisible hand at work. They might be the cosmic evidence that dark matter was not just a spectator, but an active participant in the first act of creation. The elements we are made of could hold the first clues to what the majority of the universe is actually made from. That slight matter-antimatter imbalance had a lesser-known cousin working in the shadows. While baryogenesis gave us the protons and neutrons, another fundamental asymmetry might have been at play, one involving the lightest and most elusive particles. This is the theory of lepton asymmetry. Leptons are a family of particles that include the familiar electron and its ghostly relative, the neutrino. Just as the universe favored matter over antimatter for quarks, it might have also favored leptons over antileptons. A significant lepton asymmetry would have created a universe awash with an excess of neutrinos, fundamentally changing the environment for the first nuclear reactions. In this neutrino-rich cosmos, the delicate dance that set the neutron-proton ratio would have been thrown off balance. Neutrinos interact through the weak nuclear force, and their primary role in the early universe was to constantly transform neutrons into protons and back again. An overwhelming sea of neutrinos would have pushed this transformation more forcefully in one direction. Think of it like a crowded room where everyone is trying to talk at once. The normal, balanced conversation between particles becomes a shouting match dominated by one side. In this case, a surplus of neutrinos could have forced more protons to convert into neutrons. This would have tilted the cosmic scales, leaving a greater supply of neutrons available when the 3-minute window for nucleosynthesis opened. With more neutrons on the menu, the cosmic kitchen would have cooked up a very different meal. The fusion process would have been more efficient, gobbling up nearly all the available neutrons to produce significantly more helium. The result could have been a universe with a much higher abundance of helium and a correspondingly smaller amount of leftover hydrogen. Our own universe, with its precise balance, suggests this lepton asymmetry was either incredibly small or perfectly tuned. The faint elemental fingerprints we measure today act as a cosmic veto, ruling out a reality that was too rich in these ghostly particles. This less explored pathway reminds us that the recipe for our existence depended on a quiet harmony between all the particle families, a balance struck in the first fleeting moments of everything. The precise ratio of light to matter was the final arbiter of our elemental fate. Billions of years before the first stars ignited, the universe was a brilliant, opaque sea of radiation. For every single proton or neutron, the fundamental piece of an atomic nucleus, there were over 1 billion photons, the elementary particles of light. This number, the photon-baryon ratio, is one of the most critical and finely tuned parameters in all of cosmology. It acted as the cosmic thermostat during those first 3 minutes. A higher density of photons would have meant a more intense and persistent radiation bath. This relentless light would have constantly broken apart any tentative bonds between protons and neutrons, like a strong wind blowing out the first sparks of a fire. The nuclear reactions that forged helium would have been delayed, starting later and proceeding more slowly as the universe expanded and cooled. With less time for fusion to occur, the final yield of helium would have been significantly lower, leaving behind a universe far richer in pure hydrogen. Conversely, a universe with a lower photon density would have been a darker, quieter place. The radiation pressure would have dropped much sooner, allowing protons and neutrons to find each other and fuse almost immediately. This frantic, early cooking would have consumed nearly all the available neutrons, creating a cosmos with a much higher abundance of helium. Our reality exists in a narrow window between these two extremes. The specific ratio of 1 billion photons to 1 baryon produced the exact helium abundance we observe, about 25% of the ordinary mass in the universe. This is not just a curious number, it is a direct prediction of the Big Bang model, and we can test it with astonishing precision. The cosmic microwave background radiation, the afterglow of the Big Bang itself, allows us to count these primordial photons. By measuring its temperature with incredible accuracy, we can calculate their density. Independent observations of the large-scale structure of the universe help us estimate the total number of baryons. When we compare these two monumental measurements, they align perfectly with the ratio needed to produce the elemental mix we see. This harmony is a breathtaking confirmation of our entire cosmic story. The first light elements are a permanent record of that ancient balance between the searing light of creation and the first seeds of solid matter. That ticking clock governed the universe's first nuclear reactions. A free neutron, left entirely to its own devices, is not a stable particle. It spontaneously transforms into a proton, emitting an electron and an antineutrino in a process known as beta decay. Its average lifetime is just under 15 minutes, but in the frantic early universe, 15 minutes was an eternity. The entire epoch of primordial nucleosynthesis was over in less than 3. This created a dramatic race against time. Neutrons were born in the first second, but they could not immediately form helium. the universe was still far too hot and dense, a searing plasma that instantly tore any new nucleus apart. Neutrons had to wait, and as they waited, their clock was ticking. They were decaying away, vanishing from the cosmic inventory before they could ever be used. The universe had to expand and cool to just the right temperature for deuterium, a heavy form of hydrogen, to become stable. Only then could protons and neutrons begin to form this first fragile bridge, the essential stepping stone to creating helium. This brief window of opportunity was the only chance the neutrons would get. A neutron that lived even a few minutes longer would have dramatically altered this race. With a longer lifetime, far fewer neutrons would have decayed during that waiting period. The cosmic budget for building elements would have been flush with neutrons. When the 3-minute window finally opened, the nuclear reactions would have been supercharged. Protons would have found an abundant supply of neutron partners, fusing into deuterium and then helium with incredible efficiency. The result would have been a universe with a much higher final abundance of helium. Instead of the 25% we observe, helium could have made up a third or even half of all ordinary matter. This would have left a correspondingly smaller amount of pure hydrogen as the leftover fuel. Such a shift would have rewritten the entire future of cosmic evolution. The first stars, which burn hydrogen as their primary fuel, would have had far less to consume. They would have flared into existence with a different brightness and lifespan, potentially altering the timeline for creating the first heavy elements. The delicate balance that allowed our universe to unfold would have been lost, all because of a slight change in the lifetime of a single, solitary particle. The precise 15-minute decay we measure in laboratories today was not an accident. It was a fundamental setting in the cosmic clockwork, a countdown that had to be exactly as it was for our particular universe to emerge. Our universe was not just a soup of particles, but a cosmic electrical storm. Theory 12 introduces primordial magnetic fields, powerful and pervasive forces that could have twisted the path of creation itself. Picture the early universe as a churning sea of electrically charged particles. Protons carry a positive charge while electrons are negative. In the presence of a strong magnetic field, these particles do not travel in straight lines. They are forced to spiral along the invisible lines of magnetic force like beads on a wire. This changes everything about their motion. Their paths become curved and constrained, which directly affects how often they collide. Nuclear fusion is a game of chance, dependent on particles smashing into each other with enough force to stick. If a magnetic field forces them to spiral, it could either herd them together, increasing the collision rate in certain regions, or it could trap them in isolated loops, preventing them from meeting at all. This means the formation of deuterium, that crucial first step from hydrogen to helium, might not have been a uniform process. In pockets of intense magnetic energy, fusion could have been supercharged, creating localized hotspots of helium production. In other, quieter regions, the reactions might have sputtered, leaving behind more of the basic hydrogen fuel. Even the tiny amount of lithium forged in that first 3 minutes could have been affected, its fragile nuclei potentially torn apart or its formation pathway altered by the magnetic turbulence. The idea of a magnetized beginning challenges the image of a perfectly smooth and featureless infancy. It suggests the cosmic kitchen was not just a pot on a stove, but a pot placed on a complex induction cooktop, with invisible fields creating a patchwork of temperatures and reaction speeds. The elemental abundances we measure across the sky today might not just be a relic of density variations, but also a frozen record of the universe's first magnetic fields, a ghostly imprint of forces that helped write the recipe for everything. A shadow world of particles could have rewritten our cosmic recipe. Deep within the mathematics of modern physics lies a beautiful symmetry, a theory that for every known particle in our universe, there exists a hidden, super-powered twin. This idea, called supersymmetry, is more than just an elegant abstraction. it may have had a direct and violent impact on the universe's first 3 minutes. Among these hypothetical superpartners is the gravitino, the twin of the graviton, which is itself the theoretical carrier of the gravitational force. In the incredible heat of the very early cosmos, gravitinos would have been forged in abundance. They are thought to be unstable, and their decay would have been a cataclysmic event. Imagine a quiet, organized kitchen where the chefs are carefully following a recipe. Now picture a series of firecrackers going off in the middle of that kitchen. That is what gravitino decay might have been like. As these heavy particles vanished, they would have released a torrent of energy and new particles back into the cosmic soup, a process known as reheating. This sudden injection of heat would have thrown a wrench into the delicate clockwork of Big Bang nucleosynthesis. The universe's expansion and cooling rate, so critical for timing the nuclear reactions, would have been dramatically altered. The decay products themselves could have smashed into the fragile deuterium and helium nuclei, tearing them apart as quickly as they formed. The final abundances of the light elements we see today could be a cosmic fossil, a permanent record of this hidden particle shower. The precise ratio of hydrogen to helium might be telling us that the gravitino and the entire concept of supersymmetry is not just a mathematical fantasy, but a real chapter from the very first seconds of time. The silence of dark matter might hide a gentle whisper rather than a roar. Among the many candidates for this mysterious substance, the action stands out for its peculiar delicacy. It is a hypothetical particle billions of times lighter than an electron, a wisp of a thing that could nonetheless make up the bulk of the cosmos. Its influence on the first elements would have been subtle, a ghostly hand barely touching the cosmic thermostat. The theory begins with the action field, an energy that permeated all of space in the universe's infancy. As the cosmos cooled, this field began to oscillate, and with every vibration, it produced vast numbers of actions. This process was not a violent explosion, but a quiet, persistent hum. The energy tied up in this oscillating field could have altered the very fabric of cosmic expansion. Think of the early universe as a balloon being inflated. The presence of the action field would be like changing the pressure of the air inside. If the field stored a significant amount of energy, it would have pushed back against gravity's pull, causing the universe to expand just a little faster. This seemingly minor adjustment would have had a profound consequence for the nuclear kitchen. A faster expansion means the universe cools more rapidly. The 3-minute window for nucleosynthesis would have slammed shut even sooner. With less time for nuclear fusion to proceed, the results would be clear. Less helium would form, and more of the fragile deuterium, the crucial stepping stone element, would survive without being consumed. The final cosmic budget would show a noticeable deficit. The precise amounts of helium and deuterium we measure today are so sensitive that they can rule out entire families of theoretical particles. The fact that our observed abundances align so perfectly with the standard model places a tight constraint on the action. It tells us that if actions do form the dark matter halo of our galaxy, they must be incredibly light, and their production must have been incredibly quiet. They could not have stirred the pot too vigorously, so the first light elements act as a cosmic historian, recording the gentle birth of a particle we have yet to directly see. The recipe for creation is so precise that it remembers even the lightest footstep. The universe's first instance might have been filled with tiny, ferocious knots of gravity. Primordial black holes are a theoretical possibility born from the extreme densities in that first fraction of a second. They would not have been the colossal monsters we picture today, but microscopic specks, some with the mass of a mountain compressed into a space smaller than an atom. And according to Stephen Hawking's revolutionary idea, these tiny black holes were not permanent. They would have evaporated, leaking energy back into the cosmos in a process we call Hawking radiation. The timing of this evaporation is everything. If it happened during or just after that crucial 3-minute window of nucleosynthesis, it would have been like setting off fireworks inside the cosmic kitchen. As a primordial black hole reached the end of its life, it would have released a final, intense burst of high-energy radiation and a shower of fundamental particles. This sudden flood would have torn through the young universe, striking the fragile atomic nuclei that had just managed to form. Deuterium, that delicate bridge between hydrogen and helium, would have been particularly vulnerable. Its bonds could have been shattered by the intense radiation, breaking it back down into separate protons and neutrons before it could be used to build anything else. The entire carefully balanced chain of fusion would have been disrupted. Alternatively, this evaporation could have provided a second wave of ingredients. The particles released might have offered new protons and neutrons for fusion, briefly reigniting nuclear reactions in a universe that was already cooling and thinning out. This could have led to unexpected pockets of heavier elements or altered the final, frozen ratios of hydrogen and helium we rely on as cosmic evidence. The elemental abundances we measure today could be the result of this ancient battlefield, a record of creation constantly interrupted and reshaped by the death cries of the universe's smallest and most transient monsters. Our reality of 3 spatial dimensions might be a cosmic latecomer. String theory and other advanced models of physics paint a far stranger picture of the universe's infancy. They suggest that space itself was born with more than the familiar up-down, left-right, and forward-backward we experience today. There could have been 6 or 7 additional spatial dimensions, all curled up into vanishingly small, intricate shapes at every single point. In the everyday cold of our modern cosmos, these extra dimensions are hidden, their effects imperceptible. But rewind to the first few minutes, to that unimaginable heat and density, and the story changes completely. In that high-energy forge, these extra dimensions would have been significant, unfurled and active. Their presence would have rewritten the very laws of physics, starting with gravity itself. Gravity, the force that governs the cosmos's expansion, might have been profoundly stronger, leaking into these additional directions. A universe with stronger gravity in its first moments would have expanded at a ferociously different rate. It could have ballooned out much faster, cooling so rapidly that the window for nuclear fusion slammed shut in an instant. Alternatively, the altered strength of the fundamental forces could have changed how particles interacted. The weak nuclear force, which controls the vital balance between protons and neutrons, might have operated with a different power. This would have directly shifted the neutron-to-proton ratio, the master dial for helium production. With a different starting balance, the entire nucleosynthesis process would have cooked up a completely alien set of primordial elements. Perhaps a universe with extra dimensions would have produced almost no helium, leaving a cosmos of pure, simple hydrogen. Or maybe the reactions would have been supercharged, fusing nearly all the hydrogen into helium and beyond. The specific abundances of hydrogen, helium, and lithium that we observe and measure are a permanent cosmic signature. They are a precise fingerprint that tells us our universe, when it forged its first elements, was operating with exactly 3 spatial dimensions. The recipe for creation only works in the reality we know. Those hidden dimensions, if they exist at all, had to remain tightly coiled, silent partners in a process that could only tolerate the dimensions we call home. The speed of light is the universe's ultimate speed limit, a constant so fundamental we build our entire understanding of reality upon it. But what if this rule was not always the rule? Theory 17 dares to suggest that in the frantic first moments, light itself raced across the cosmos at a different, far faster pace. The constancy of light speed is the glue that holds our modern physics together, ensuring that cause and effect are connected and that the universe can reach a uniform temperature. If light could travel faster in that initial firestorm, it would have rewritten the basic script of creation. different regions of the infant cosmos would have fallen out of contact with each other much sooner, like islands drifting apart before they could agree on a common climate. Without this constant communication, the universe could not have thermalized perfectly. Some pockets would have remained hotter and denser, while others cooled more rapidly, creating a patchwork of different environments before nucleosynthesis even began. This would have meant a cosmic kitchen with no single recipe. In a hotter, denser region, the nuclear reactions would have roared ahead, fusing hydrogen into helium with incredible efficiency and leaving very little of the fragile deuterium behind. In a neighboring, cooler patch, the process would have been sluggish and inefficient, resulting in a much higher abundance of leftover hydrogen and deuterium. The primordial elements would not have been stamped out in a single, identical mold. Instead, the universe would have been born with a unique chemical fingerprint in every direction, a fundamental lack of uniformity written into its very first atoms. The consistent elemental abundances we observe from one galaxy to the next, one of the strongest pillars of the Big Bang theory, would become a mystery. The fact that we see such a uniform spread of hydrogen and helium today is a powerful argument that the speed of light was indeed constant, locking the universe into a single, coherent story from its very beginning. The first light elements are a permanent record of that foundational constant, a testament to a rule that could not be broken. Perhaps the Big Bang was not a single, definitive birth. The ekpyrotic universe theory offers a breathtaking alternative where our entire cosmos exists on a vast three-dimensional membrane or brain floating within a higher dimensional space. In this model, the violent beginning we call the Big Bang was not the start of everything. It was a rebirth, a collision between our brain and a neighboring parallel universe. This cosmic crash infused our reality with the immense heat and energy we mistake for a singular creation event. Before this collision, our universe existed in a cold, contracted state, a quiet prelude to the firestorm. This pre-bang history is not lost. It could have imprinted itself onto the very first atoms. The conditions during that slow, cold contraction phase would have been entirely different from a traditional Big Bang singularity. The distribution of energy and the initial vibrations of fundamental fields would have carried a unique signature into the new cycle. When the brains collided and our universe was reborn in a flash of heat, the subsequent nucleosynthesis did not start with a perfectly clean slate. It inherited a specific set of initial conditions from the previous cosmic cycle. The process of primordial nucleosynthesis would have unfolded with a subtle bias, a ghostly memory of a time before time. The specific ratios of hydrogen to helium, or the tiny amount of lithium forged in that first 3 minutes, might not be purely the product of a single, isolated event. They could be a palimpsest where the chemical fingerprint of our current universe is written over the faded echoes of a previous one. Imagine finding a family recipe passed down through generations where each cook has added their own slight twist. The final dish you taste today carries the history of every hand that prepared it before. In the same way, the elemental abundances we measure with our telescopes might be a cosmic recipe perfected over countless cycles of collision, expansion, and contraction. This theory forces us to reconsider the very meaning of a first impression. The first light elements we study may not be the first at all, but merely the latest iteration in an infinite loop of cosmic renewal. The very expansion of the universe is the bedrock of our cosmic story, but what if that bedrock is an illusion? Theory 19, the tired light hypothesis, pulls this foundational block away. It dares to suggest that the universe is not flying apart at all, but is instead static, eternal, and ageless. The famous redshift of distant galaxies, the key evidence for an expanding cosmos, is reinterpreted. In this view, light does not stretch because space itself is stretching. Instead, photons simply grow tired. They lose energy during their immense journey across the void, slowly reddening from sheer exhaustion over millions of light years. This single change in perspective unravels the entire narrative of a beginning. If the universe has always existed, then there was no Big Bang, no initial fireball, and crucially, no 3-minute window of primordial nucleosynthesis. The cosmic kitchen never existed. This leaves a monumental puzzle. How then do we explain the universal abundance of hydrogen and helium, the very fingerprints that seem to point directly to a hot, dense birth? Proponents of a static universe must find another cook. One possibility is that stars themselves have been the universe's only forge. Over an infinite amount of time, countless generations of stars could have fused hydrogen into helium, eventually enriching the cosmos to the levels we see. But this faces a severe challenge. The oldest stars we observe, those born long before our own sun, already contain that primordial mix of about 75% hydrogen and 25% helium. There would not have been enough time, even in a vastly old universe, for the first stars to produce and distribute such a uniform blanket of helium before the next generation formed. Another, more radical idea is some form of continuous creation, where hydrogen atoms simply pop into existence in the empty spaces between galaxies and then are slowly processed over eons. Yet this introduces more mysteries than it solves. The tired light hypothesis represents a fundamental departure, a complete rewrite of cosmic history where the first light elements are not a relic of creation, but a symptom of an endless, steady-state cycle. The precise recipe of hydrogen and helium that our universe follows so perfectly becomes, in this view, not the opening chapter of a story, but a permanent, unchanging condition of reality itself. Gravity may not be the universe's primary architect. A radical perspective known as plasma cosmology shifts the cosmic spotlight from the silent pull of mass to the visible crackle of electric currents. This framework envisions a cosmos without a singular birth, an eternal and infinite expanse where the story of the first elements is not a one-time event but an endless cycle. The primordial ingredients of hydrogen and helium are not relics of a 3-minute forge. Instead, they are constantly being cooked and recooked inside colossal plasma filaments that stretch between galaxies. Picture these filaments not as simple strands of gas, but as cosmic-scale power lines carrying immense electrical currents across the void. Within these twisting, dynamic structures, the intense electromagnetic forces can tear atoms apart and slam particles together with ferocious energy. This continuous, chaotic process of ionization and recombination becomes the true engine of elemental creation. It is a universe where the kitchen is always open and the recipe is written in lightning. This view completely reimagines the evidence we take for granted. The cosmic microwave background, often called the echo of the Big Bang, is reinterpreted as the thermal glow from countless currents coursing through interstellar dust. The uniform spread of light elements across the cosmos is not a fossilized fingerprint from a single instant, but a sign that this electrical processing has reached a steady state, a dynamic equilibrium that looks the same in every direction because the underlying forces are universal and eternal. The question then becomes not how the elements were first made, but how they are perpetually renewed. This challenges the very core of our cosmic origin story, suggesting that the atoms we are made of were born not in a moment of definitive creation, but in the endless, shimmering dance of electricity across an ageless universe. This precise recipe of hydrogen and helium forces a question that echoes far beyond cosmology. Why do the fundamental constants align so perfectly to create a universe with stars, planets, and life? The anthropic principle offers a staggering answer. It suggests our entire cosmic story is not a matter of destiny but of sheer mind-boggling chance. Imagine a cosmic lottery with an infinite number of tickets, each representing a different universe with its own unique set of physical laws. In nearly all of these universes, the numbers are wrong. The weak force is too strong and almost no helium forms, leaving stars without the fuel to burn long enough for life to evolve. or the photon density is too high and nuclei never bind, creating a permanent fog of disconnected particles. In another, the imbalance between matter and antimatter never occurs, and the entire universe annihilates itself into nothing. Our universe is the one in a Google winning ticket. It is the rare bubble where the neutron lifetime, the force strength, and the expansion rate all conspire to produce a specific mix of 75% hydrogen and 25% helium. This is not a special mix. It is simply the only mix that allows for a cosmos old enough and stable enough to eventually ask questions about its own origin. The hydrogen is plentiful for forming water, the universal solvent of life. The helium is essential for the long, steady fusion in stellar cores, providing the billions of years necessary for planetary formation and biological evolution. We are not here because the first elements were forged in a uniquely special way. We are here because in a vast and mostly barren multiverse, this is one of the vanishingly few versions where the first 3 minutes produced a result that allowed for observers. The atoms in your body are not just relics of a cosmic beginning. They are the ultimate survivors of an unimaginable selection process, the necessary ingredients for a universe that can look back upon itself and wonder. There is a wall at the beginning of time that our physics cannot yet cross. Before the universe was even a second old, before a single proton could form, the cosmos was compressed into a volume so small and dense that the very idea of space and time loses all meaning. This is the Planck epoch, a realm where gravity was no longer a gentle curve in spacetime but a seething, chaotic foam. In this quantum gravity regime, the fabric of reality itself was subject to violent fluctuations. Spacetime was not a smooth stage but a turbulent ocean, with microscopic black holes and wormholes bubbling in and out of existence. In this environment, the rules for how particles interact would have been rewritten. The fierce energy of these spacetime tremors could have directly intervened in the nuclear reactions struggling to begin. A quantum ripple in the geometry of the universe might have delivered a burst of energy so precise it could fuse a proton and neutron into deuterium an instant before the standard model would allow. Conversely, another fluctuation might have torn a newly formed helium nucleus apart, not through a particle collision, but by twisting the very space it occupied. The first atomic nuclei were not just assembling in this foam, they were part of it. Their stability depended on the calmness of a sea that was fundamentally wild. The final, frozen abundances of hydrogen and helium we measure today could therefore be a cosmic fossil of this deepest layer of reality. They might encode the signature of how spacetime itself behaves when it is pushed to its absolute limit. This theory suggests that the recipe for the first elements was not just set by particle physics, but was co-authored by the quantum nature of gravity, a force whose deepest secrets are still locked within those first traces of helium. Our universe might be a rebound from a previous collapse. The pre-Big Bang cosmology dares to ask what happened before the beginning, proposing a cosmic cycle of contraction and expansion. Imagine the entire universe not exploding from a single point, but rather springing back from a state of immense density, like a ball bouncing after being squeezed with infinite force. This is the bouncing universe model, and its implications for the first elements are profound. The conditions of that pre-bounce phase, the state of the universe as it contracted towards its point of maximum density, would not have been erased. They would have been carried over into the new expansion, setting the initial stage for everything that followed. The specific vibrations and density patterns present just before the bounce would have been the true starting point for nucleosynthesis. The 3-minute nuclear cooking session did not start with a perfectly clean slate. It began with a specific set of inherited ingredients, a cosmic recipe that was already partially written. This means the precise ratios of hydrogen to helium we measure today might not be purely a product of our expanding universe's physics. They could be a legacy, a chemical fingerprint passed down from a previous cosmic era. The tiny amount of lithium or the specific abundance of deuterium could be a coded message, a relic from the universe that was before our universe began. This theory transforms the first light elements from simple relics of creation into cosmic archaeologists. They are not just telling us about the first 3 minutes of our cycle, but potentially offering a glimpse into the cycle that came before. The atoms in every star are not just ancient, they might be eternal, carrying a story that stretches back into a time before time itself. The universe may be a hologram. This is not science fiction, but a serious proposal known as the holographic principle. It suggests that all the information contained within any three-dimensional volume, including every star, planet, and person, can be perfectly encoded on a two-dimensional surface that surrounds it, like a cosmic barcode printed on a sphere. If this is true for our universe today, what does it say about its first moments? Apply this mind-bending idea to the dawn of time, to that frantic 3-minute kitchen where the first elements were forged. The entire fiery, three-dimensional drama of protons and neutrons colliding and fusing might not have been the fundamental reality. Instead, it could have been a projection, a holographic movie playing out according to a script that was written on the two-dimensional boundary of the infant cosmos. The ingredients themselves, the hydrogen and helium, would not be independent actors. Their final abundances would be deeply intertwined, connected by mathematical relationships imposed by the holographic code. In our standard three-dimensional view, we calculate the amount of helium based on the expansion rate and the neutron supply. But from a two-dimensional perspective, the quantity of helium might be mathematically locked to the amount of deuterium or lithium in a fixed, precise ratio that our ordinary physics cannot see. This principle could reveal a hidden unity in the primordial recipe. The specific percentages of these light elements we measure today would not be a collection of separate outcomes, but different facets of a single, elegant piece of information projected into the volume of our universe. The cosmic fingerprint we have been studying for decades might actually be a shadow, a holographic echo of data stored on the surface of a reality we cannot yet perceive. A hidden, parallel reality could have been tugging on our universe from the very first second. The mirror matter hypothesis introduces a cosmos with a perfect, unseen twin. This is not science fiction, but a serious proposal that for every particle we know, from the humble electron to the bustling quark, there exists a mirror copy. These shadow particles would form their own atoms, their own chemistry, and even their own stars and galaxies, all completely invisible to our eyes and our instruments. The only thread connecting our world to this mirror realm is the faintest of all forces, gravity. In the primordial fireball, this mirror sector would have been just as real and active as our own. While our protons and neutrons were fusing into hydrogen and helium, their mirror counterparts were undergoing an identical process of mirror nucleosynthesis in a parallel, overlapping kitchen. The gravitational pull of all that mirror matter, however, would have been a constant, subtle presence. It would have acted like an invisible weight, altering the expansion rate of our familiar cosmos during those critical first 3 minutes. A universe expanding under the additional gravitational burden of a mirror twin would cool at a slightly different pace. This shift in timing is the key. If the presence of mirror matter made the universe expand just a fraction faster, the nuclear reactions would have been cut short, leaving more fragile deuterium unconsumed and producing a little less helium than expected. If it slowed the expansion, the opposite would occur, with fusion proceeding more efficiently. The fact that our observed elemental abundances fit the standard model so perfectly places a tight constraint on this idea. It tells us that if a mirror world does exist, its gravitational footprint had to be incredibly light, or its properties almost perfectly aligned with our own. The precise recipe of the first light elements becomes a cosmic detective, ruling out entire classes of hidden universes that would have tugged a little too hard on our own creation. Mass itself may be the universe's greatest illusion, a trick played by a field we call the Higgs. But what if this is not the only way particles could have gained their substance? The Technicolor theory proposes a radical alternative where mass is not granted by a singular field, but is instead forged through a new, powerful force of nature. Imagine the familiar strong force that locks quarks together inside a proton. Now picture a similar but far more potent interaction that existed only in the universe's fiery infancy. This Technicolor force would have acted on a whole new family of particles, the techni-fermions. In the searing heat of the first moments, these particles would have been bound together into composite states, much like quarks are bound into protons. The formation and subsequent decay of these technihadrons would have been a spectacular event. As the universe expanded and cooled, these composite particles would have broken apart, releasing a tremendous burst of energy back into the cosmic soup. This is not a gentle whisper, but a sudden shout that echoes through the thermal history of everything. This release of energy would have reheated the cosmos, effectively hitting the pause button on its cooling rate. The clock governing the universe's expansion would have been reset, altering the precise timeline for the formation of the first atomic nuclei. The 3-minute window for nucleosynthesis would have been shifted, starting later or ending sooner than in the standard model. This could have profound consequences for the final recipe. A delayed start might mean fewer neutrons decay away before fusion begins, leading to a higher final abundance of helium. Alternatively, an earlier shutdown could leave more of the fragile deuterium intact, as there is less time for it to be consumed in the chain reaction that builds helium. The Technicolor scenario offers a potential solution to some of the small, lingering mismatches between the predicted and observed light element abundances. It suggests that the Higgs mechanism we are searching for in our particle colliders might not be the full story, the true origin of mass, and by extension the precise conditions that allowed our elemental mix to form, could be tied to a forgotten primordial strength that has long since faded from the universe. The moment the universe chose its identity is written in the first atoms. Right before nucleosynthesis began, a fundamental separation occurred. The electroweak force, a single, unified power, split into the two distinct forces we know today: the electromagnetic force that governs light and chemistry, and the weak nuclear force that controls radioactive decay. This was the electroweak phase transition, and its precise character was critical. If this transition happened suddenly and violently as a first-order phase change, it would have been like the universe freezing over in an instant. Think of a lake flash freezing, with sheets of ice crashing into one another. In the cosmic context, this violent shift would have sent powerful ripples through the fabric of spacetime itself, gravitational waves echoing from the first second. These waves would have churned the primordial plasma, the hot soup of particles waiting to form the first nuclei. This churning would have created a turbulent sea of dense lumps and thin voids, dramatic inhomogeneities in the infant cosmos. In the denser regions, where protons and neutrons were packed tightly together by the turbulence, nuclear fusion would have been supercharged. These local hotspots could have cooked hydrogen into helium with frantic efficiency, potentially creating pockets with a much higher helium abundance than the cosmic average. Conversely, in the thinner regions stirred up by the chaos, fusion might have sputtered, leaving behind more of the basic hydrogen fuel and the fragile deuterium. The very uniformity of the elemental recipe we see across the sky hinges on this transition being a gentle, smooth crossover, not a violent upheaval. A calm separation would have left the plasma mostly undisturbed, allowing for the even cooking the standard model describes. The specific, consistent ratios of light elements we measure are a silent witness, testifying that the universe's fundamental forces parted ways with a whisper, not a bang, ensuring a stable and predictable foundation for all that followed. A silent web of cosmic cracks may have stirred the primordial soup. Theory 28 introduces cosmic strings not as the building blocks of atoms, but as unimaginably dense flaws in the fabric of spacetime itself. Picture the early universe cooling through a critical phase transition, like a sheet of glass rapidly solidifying. As it set, tiny imperfections could have been frozen into its structure, stretched into one-dimensional filaments of pure energy. These were not strings you could cut. Each one would have been thinner than a proton, yet a single inch of its length could contain the mass of an entire mountain range. This network of cosmic strings would have thrummed with violent energy, slicing through the hot plasma of the early universe. As they vibrated and looped, they would have created powerful shock waves, like the wake of a speedboat cutting across a still lake. These waves compressed the surrounding soup of particles, squeezing protons and neutrons together with immense force. In the turbulent wakes of these cosmic filaments, the conditions for nuclear fusion could have become supercharged. The Standard Model struggles to explain the precise amount of lithium we find in the oldest stars, but in the high-pressure zones trailing a cosmic string, the delicate nuclear reactions that create and destroy lithium could have been pushed into overdrive. A passing string might have provided just the right catalyst, a fleeting surge of density that forged a tiny excess of this fragile element before the universe cooled beyond the point of fusion. The specific abundance of lithium we observe today might not be a simple product of a uniform expansion. It could be the scattered signature of a vibrating web, a fossil record of spacetime's imperfections written in the oldest atoms. Gravity is the weakest of the fundamental forces, a gentle pull we barely notice in our daily lives. Yet its constancy is the metronome that kept time for the entire cosmic symphony of creation. But what if gravity itself was not always so weak or so constant? Brain-world nucleosynthesis explores this unsettling possibility. In this theory, our entire universe of 3 dimensions is just a thin membrane, a brain, adrift within a vast, higher-dimensional expanse called the bulk. We are stuck on this membrane, unable to perceive the other dimensions directly, but gravity is different. It is not confined to our brain, it can leak. In the early universe, this leakage would have been dramatic. A significant portion of the gravitational force generated by all that primordial energy could have seeped away into the higher dimensional bulk, effectively diluting its strength within our own reality. From our perspective, trapped on our 3-dimensional sheet, gravity would have felt weaker. The consequences for the first elements would have been immediate and catastrophic. Gravity's pull directly controls how fast the universe expands. A weaker gravitational force in that first second would have unleashed a runaway expansion. The cosmos would have ballooned outward at a ferocious pace, cooling so rapidly that the nuclear kitchen would have been shut down almost before it opened. The window for protons and neutrons to find each other and fuse would have slammed shut in an instant. The result would be a universe almost entirely composed of hydrogen, with only the barest, undetectable trace of helium and no lithium at all. Conversely, if the geometry of the bulk caused gravity to be concentrated onto our brain, making it stronger, the opposite would occur. A more powerful grip would have held the universe back, slowing its expansion to a crawl. This would have given the nuclear reactions far more time to proceed, consuming nearly all the available neutrons to produce a cosmos drowning in helium. The delicate balance we observe, the specific recipe that allowed for stars and planets, hinges on gravity behaving exactly as it does in our laboratories today. The fact that our universe cooked up 25% helium is a powerful piece of evidence. It suggests that in those first 3 minutes, gravity was not leaking away into other dimensions in any significant way. The force that shapes the cosmos had to be present in full strength, holding the universe to a precise and measured pace, a tempo perfectly set for the forging of our future. The final theory takes us to the edge of physics and philosophy, proposing that the universe is not made of fields or particles, but of information. From this radical viewpoint, every law of nature, including the precise nuclear physics of the first 3 minutes, emerges from a deeper, computational layer of reality. The cosmos is not a machine, it is a computation. Within this framework, the specific recipe of 75% hydrogen and 25% helium is not a random outcome of expansion and cooling. It is the output of a cosmic algorithm, a set of instructions running on the hardware of spacetime itself. This algorithm might have been optimizing for a specific cosmic goal, such as maximum stability or the potential for future complexity. Hydrogen, in its beautiful simplicity, is a stable and versatile information carrier. Helium, with its tightly bound nucleus, offers a stable stepping stone, a crucial piece of code that allows for more complex processes like stellar fusion to later emerge. Even the tiny, problematic amount of lithium could be a necessary byproduct, a line of code required to prevent logical contradictions in the cosmic program. What we perceive as the fundamental forces of nature could be high-level user interfaces, convenient abstractions that hide the raw data processing happening beneath. The frantic dance of protons and neutrons in the primordial fireball was not governed by blind chance, but by a deep computational necessity. This transforms the first light elements from cosmic fossils into a permanent, running script. The hydrogen in a distant nebula and the helium in a newborn star are not just chemicals. They are lines of code in a program that has been executing for 13.8 billion years. A program whose ultimate purpose might be to generate the complex structures like galaxies and minds, capable of reading its own source code for the very first time. Our journey through 30 cosmic recipes has reached its end, from the solid ground of the Big Bang to the speculative shores of holograms and bouncing universes. Each theory, whether anchored in data or soaring on imagination, represents a profound human effort to answer one of existence's oldest questions: where did the stuff we are made of truly come from? The standard model of primordial nucleosynthesis gives us a powerful and tested foundation, a 3-minute window that explains so much of what we see. Yet the wilder ideas, from ghostly neutrinos nudging the balance to cosmic strings stirring the pot, remind us that the story is not yet complete. They challenge our assumptions and push the boundaries of what is possible. This is not a search with a single destination. It is an ongoing conversation between theory and observation, a cosmic detective story where the clues are written in the oldest stars. The helium in a distant galaxy and the hydrogen in a vast nebula are more than just fuel for stars. They are ancient texts, and we are only just learning how to read them. So we turn the question back to you. After exploring these 30 paths, which vision of the beginning feels most compelling? Does the elegant simplicity of the standard model speak to you, or does the chaotic potential of a lumpy universe fire your imagination? Perhaps the idea of a cosmic computation or a holographic projection resonates more deeply. The conversation does not end here. Share your favorite theory in the comments below and let us know what cosmic mystery we should explore next. If you enjoyed this deep dive into the dawn of time, subscribe for more journeys to the edge of our understanding, and never forget the incredible truth written in your very cells. Every atom in your body, every breath you take, was once forged in the universe's first